One of the things you would like to do is to actually plan using proton imagery rather than X-ray imagery, which is what we do now. And this is really because protons and photons react differently, stop differently. But imaging with protons is difficult. So we've built a machine. We're not the first in the world, but we're the first to do it in an integrated fashion and to build it totally solid state. So we record the trajectory of every proton coming into a patient and the trajectory of every proton coming out of the patient and what energy is left in the patient, left after the patient. So we work out what's deposited in the patient. And from that we can develop the stopping power Proton CT map. Yeah, it weighs over a ton. It will not be like that in practice. And you can see, I showed in the odd slide of the Fermilab's one. I mean, theirs is even worse looking than ours. Yeah, I mean, it's a prototype, it's not a commercial machine. We'll get it down much tighter. If some of the things spoke about today, how we can do CT and not have this expensive range telescope, this thing that measures the residual energy of the protons that go through the patient, then you could make a very compact system. And you would build that into the couch and into the gantry or whatever the delivery system is. It'd be more compact than a typical cone beam X-ray system. One or two groups around the world, including ourselves, I think have demonstrated that Proton CT is possible, the quality is there, and it's now engineering, if you like, a commercial prototype, and then going on to trials and so on, getting it into application. I think 3 years. Certainly what I think is required is much better instrumentation, that we know what we're doing. We understand now not just the advantages of proton therapy, but also its limitations in how we can distribute dose. But we need to monitor that in real time. During treatment, to replan at frequent intervals, to compensate for anatomical changes, patient movement, everything else. And then, as I say, we can provide optimum treatments and not just what we have to do now as robust ones. Well, I'd like to think you're right. I think we've also shown that something which is technically difficult is possible, that we are beginning to show that there is a whole new field of charged particle imaging, not just protons, but perhaps other charged particles as well. And there are a variety of ways we can get these images using the properties of the protons or the other charged particles, and how we fuse that with, like, conventional images. That's a whole new field. Yeah, and an exciting one, and one I think will make a great deal of difference. There's been a serious effort to bring together quite a representative group of leading experts in the world. So if you like, I'm the one imaging expert here, and that's useful because I don't really have to argue with any other imaging experts. That's always an advantage. So it's good to meet people from other groups, and there's other aspects, and there's quite a few of the guys I know anyway, so it's good to catch up. We have some opportunities at the moment to potentially commercialize what we're doing. We have to optimize many aspects of it. We have to take into account new delivery systems, pencil beam systems. In the longer term, if you like, if you call it the software side, we have to see how we can make use of all these different proton CT images, how we can merge them together, how we can fuse them with other types of imagery, X-ray imagery. So it's the beginning of a whole new field of, if if you like, charged particle imagery. And then beyond that, we'll probably look at helium, because helium has many advantages, potential advantages for treatment, and our even prototype equipment could be used to image helium, and we've got access to some helium beams, but I don't think anyone's going to throw away their multi-million-pound investment in protons for helium just yet.